Our work tackles the problem of estimating accurate surface normals from a single image of a human face in the wild, with the goal of enhancing an existing coarse reconstruction. This line of research aims at reducing acquisition constraints in 3D facial capture and has applications in animation, special effects, telepresence, and human digitization, among others. Monocular face reconstruction is an ill-posed problem which requires strong prior knowledge. In this regard, shape-from-shading-based methods have limited applicability to images in the wild due to simplified image models. The reduced dimensionality of parametric shape models that makes them robust hinders, on the other hand, their ability to capture fine details. Another family of work casts the problem as an image-to-image translation using deep learning. While directly regressing depth can yield suboptimal results due to scale ambiguity, especially detail-wise, regressing normals appears to be an easier task for neural networks, given that normals are strongly correlated to pixel intensities and depend mostly on local information. The main obstacle here remains lack of training data, especially images in the wild with corresponding fine, detailed 3D ground truth. We propose to overcome this obstacle with a new architecture that combines the benefits of cross-modal learning and skip connections. We start from an encoder-decoder architecture that maps images to normals. The architecture can be improved in two ways. Skip connections can be added to transfer details from the image to the normal domain. To counter the lack of image normal data supervision, we can improve the latent space by adding an auxiliary normal encoder and image decoder, which allows training with additional unpaired color and normal images. To combine these two improvements without hampering the architecture, we need a new type of skip connections that can be activated when translating images to normals and deactivated when auto-encoding normals. We call them the deactivable skip connections. Instead of concatenating the encoder features in red and decoder features in blue, as with standard skip connections, we fuse the encoder features with part of the decoder features in light blue using an element-wise max operator to be able to deactivate this operation when needed. We train our architecture with the L2 reconstruction loss for color image outputs and the cosine distance to ground truth for normal image outputs. For datasets containing only color images, namely Celebay HQ, we train the network by backpropagating the loss of the image-to-image translation task. For datasets containing only normal images, namely BGUT, we train the network by backpropagating the loss of the normal-to-normal translation task. Finally, for datasets containing images with paired ground truth normals, namely ICT and photoface datasets, we start with a normal-to-normal pass, followed by averaging the losses of the image-to-image and image-to-normal translation tasks. We perform an ablation study that shows the benefits of each component of the final architecture both numerically and visually, as our model seems to get the best from each of the alternatives. The cross-modal model, without skip connections, appears smoother and lacks details. Removing the normal encoder yields less accurate shape representations, since the model learns less information on facial geometry. Removing the image decoder gives poor results for images in the wild, due to the domain gap between training and evaluation. We compare against state-of-the-art methods that either estimate normals or 3D reconstructions. We obtain state-of-the-art results in the photoface and Florence datasets in terms of mean angular error and percentage of normal pixels under 20 degrees. Our good performance is also confirmed by qualitative comparisons over images in the wild in various head poses and under arbitrary lighting conditions from the 300W dataset. For both our approach and SFSNet, we show the normal mapping over the same base mesh obtained using PRN. We show our meshes from two viewpoints to illustrate that the output is not optimized for a particular viewpoint, a known limitation with shape from shading. Thanks to our normals, we recover much more refined and accurate geometric details compared to the competition. We show here an additional example application on the face warehouse dataset where raw depth obtained from a commodity sensor can be enhanced with the normals obtained from the color images using our method. Thank you all for watching.